service-based prototyping of embedded systems.
Yes, hello. Everybody can hear me, and I am pleased to represent this work by the Jacdac team. It's done over the last 4 years or so, including a number of people from Microsoft and Steve Hodges, who is now at Lancaster University in the UK. So we heard a lot about Moore's Law today and through the years. I'm going to tell you a little story about that and Jacdac and how we got to this weird plug-and-play system, which is actually commercially available and will be handed around for you to try. A very interesting sort of demo. So Moore's Law has enabled just so much. At Microsoft, we piled on features and features in the software. We got layers of abstraction. We're able to virtualize pretty much every piece of hardware known to man because computers are so powerful. And people think of it as over, but on the low end, it's not. So microcontroller-based technology, which is low power, low cost, is actually several generations back. And it's getting more and more powerful, smaller. And so Moore's Law is not dead yet at the low end. However, if we think about prototyping with microcontroller-based technology, it is really stuck in the 80s. We have I2C, SPI, fiddly wires, fiddly connectors, and especially if you're trying to get new people to start working with microcontrollers, it can be quite a bit of friction. So the basic idea of Jacdac, very simply, is to use extra silicon close to devices, like even buttons, plus a modern software stack to make it easier to prototype embeddable devices with microcontrollers and to make that as widely available as possible. So the overview of the talk, I'm going to give you a little background of where I'm coming from. Over the last 8 years, my team at Microsoft has worked with the BBC, and we've created a system called the microbit with a programming environment. The microbit is a small board, and it's very low cost and high quality, and the programming environment and the materials for teachers make it simple to learn and use, and it's been around for 8 years now, primarily in middle school. As software engineers and software engineering researchers, we also want to make the experience extensible, and that's where we sort of give it a thumbs down. So Jacdac, you can think of it as plug and play for microcontroller-based technology, much like USB allows us to plug things into our computers every day, and it just works, mostly. So what is this idea of physical computing? Physical computing is actually the term that educators use for software and hardware that senses and responds to the real world. So in PLDI talk, that's embedded or reactive systems generally. Maybe not hard real-time systems, but anything that can sense environment, the light, sound, and can react to it through actuation, that can be a physical computer. And that's a great way to actually get many types of people engaged in computing through things that actually move and shake and make sound. Yeah. So one physical computer that came out in 2016 is the BBC Microbit. I'm actually showing you here version 2. It's about half the size of a credit card. On the front side, you'll see an LED screen, 5x5, so very high-res graphics with 2 buttons, A and B, and an edge connector at the bottom. On the back, there's a whole bunch of things like a compass and an accelerometer. There's a radio antenna. It speaks Bluetooth and a lower-level protocol, essentially UDP. It has a microphone and a speaker, and it has a processor now with a whopping 128 kilobytes of memory. That's 3 times what my Apple II from 1981 had. It goes a little bit faster. I think it's clocked around 64 megahertz, and it has half a mega flash. So it's an awesome computer to learn with, and it's visible, unlike many of the computers that are sealed away in consumer products. The microbit is a visible computer. And what can you make with it? Well, since it's battery powered and very low power usage, you can strap it to your foot and you can make a step counter. You can make a rock, paper, scissors game where you shake the microbit and play rock, paper, scissors against your digital opponent. You can also make crazy robots that respond to light and actuate servos. So, you know, the microbit is a little embeddable computer that can be programmed, and there's a lot of creative uses. Here, we're showing the microbit in a radio control car situation. So you have 2 microbits, and the accelerometer on the one in the person's hand is being used to send messages to the microbit, which is, you know, driving the car. So you can also do sort of remote control and that. We premiered the microbit, we premiered in the UK in 2016. Since then, the Microbit Education Foundation is a nonprofit that took over the brand. Its goal is to inspire every child to create their best digital future, and there's over 8 million microbits distributed worldwide today in over 60 countries. The cost of the microbit is under $20, so it's quite cheap, and they're commercially available, so you can find them pretty much in Amazon or everywhere. My team at Microsoft, we created this platform for programming microcontroller technology using web apps. So no C compiler required, no download, no install on a computer by an IT admin. And then we've with partners, we've surfaced several websites. The web app basically has a full IDE with both block-based programming a la Scratch and JavaScript, and you can go between blocks and text-based coding. That's novel. It's all written in TypeScript, and it features both hardware simulation and a compiler all the way to ARM machine code in the browser linked against a pre-compiled C++ runtime. So once the web app is loaded, you're good to go. There's no call out to a C or C++ compiler. And we've actually got a number of different websites that are hosting different types of microcontroller-based hardware. On the left, the microbit; in the middle, the Adafruit Circuit Playground, and then we have a special thing for retro arcade games on the right that's near and dear to my heart. The principles of Make Code are to really simplify making and coding with microcontrollers, meet educators and students where they are, which would be Chromebooks, Mac OS, Linux, Windows, whatever has a modern web browser. How's that for Microsoft? And support progression to a wider world of programming languages such as JavaScript. We also support Python. And really this idea of actually extending beyond what's possible with the microbit to peripherals. And that's where this idea of extensibility comes in. So let's go to a demo. I will very quickly show you what it's like programming inside Make Code. And for some reason, we are not seeing that on the screen. No, I don't know. It has not happened. Usually I'm just duplicating my screen. Let me just duplicate. We're good? Okay, I'm getting out of that, and I have no idea why we wouldn't be seeing this. Okay, there it is. So Make Code, this is Make Code with a little program that I've created, which basically has 3 blocks that you can drag out. On button A, we show a heart. When we press the logo, we clear the screen. So I can do that by touching in the simulator here. And then on button B, we do something different. We show the current temperature. And of course, what's the temperature? Well, it's actually simulated here. So the current temperature, let's drop it. Let's drop it to the single digits and press button B again. It's now 7 Celsius. Brr, I'm cold. Okay, so this is essentially the programming environment. We can go to JavaScript. We can actually do text here. We can go back to blocks. There's a whole bunch of features I can't get into. But extensibility. So let's say I'm a teacher, and I'm like, oh, this is great. I have this ability, but I want my students to learn about the environment. So what hardware is out there? So we go here, and we search in the extension dialog for environment. We see all these partners who have all this cool hardware, and we click on one, and now it's loading an extension, a library, into the environment. And now I can see here, oh, I can get the air and weather, and oh, I can get, oh, not just temperature, I can get humidity. So let me drag humidity and put that there instead, and then run my program. And now we sort of see the problem. We get like a question mark, right? That hardware, we don't know about the hardware, we just have some code. And that code basically is, oh, you read the temperature from this GPI pin, or you read it over I2C. But we don't have support for that. So whenever we add hardware to the mix, unless we special case stuff, this whole beautiful experience of coding with the simulator and then downloading the code, which I haven't shown you, there's the compiler. We can download its file. And now that compiler in the browser is being invoked, and voila, we just got a hex file which we could drag and drop onto the device. So the problem there is that we've got extensibility in the software domain, but not in the hardware domain. Okay, and that's really where we come back then to Jacdac, which is this plug-and-play system. So we think of USB as an exemplar of plug-and-play. Why? You have standardized cables and connectors. You have dynamic discovery and composition with devices, and you have abstraction over common devices. The cons are that USB is not really a true bus. Connections are point-to-point. A host is required for direct communication. And the cables and connectors are much more bulky and rigid than what you find with prototyping. So it all leads to higher cost. So with Jacdac, what we're doing is trying to get a lot more pros. We got the first three things: standardized cables and connectors, discovery, abstraction. But we have a true bus architecture, low cost relative to USB, and a very easy programming paradigm, as you'll see. The cons are low bandwidth. It's 1 megabit per second. And there's an increased cost on the edge, as you'll see. But it's very low, about 3 cents for an 8-bit PLDI processor. So the Jacdac connector and cable are shown here. It's built into the PCB, so it's part of the PCB design. It's got ground, power, and data. The data is the short one. It's double-sided. So then the connector, the cable, it doesn't matter which way you put the cable in, it connects, and here are the cables. The modules are very simple. They range from buttons to sliders to a light detector in the middle, and you'll see the Jacdac connector on each of them. Furthermore, you'll see a very tiny little integrated circuit. That's the PLDI. That's the extra silicon we're spending to actually have each device be able to advertise itself on the bus. Okay, so what I'd like Blake to do is plug the battery in to the device we have there, which has been loaded with a little jukebox program, and you can hand it around and try plugging and unplugging devices and play with them and see what happens. You've got the microbit, essentially. What is being handed around there is the microbit with an adapter to Jacdac, and then this is the cable, and you can see the plug. So please hand that around. Feel free to play with that. Okay, so this is a really weird idea, but we view Jacdac as a client-server architecture where everybody's on the same bus, and there can be both modules, which are servers. Like a button is a server now that says, I'm a button, I can be pressed, and you can use me. And then there are brains, our clients, that are the user level programs. So in the case where we use Jacdac with the microbit is the brain, it's the client, and then we have a true bus, everybody's on the same 3 wires, and the modules at the bottom, here from left to right, an accelerometer, a light sensor, a slider, and an LED ring, are the servers. Okay, and they're all advertising themselves and saying, hey, I'm here, I'm alive, and this is the service that I represent. So if you think of this in terms of an OSI stack on the left, Jacdac has a number of similar levels to OSI, but we've defined from bottom up an electrical or a manufacturing and mechanical design, electromechanical attributes, and electric. That's for another paper. The PLDI paper focuses on really the software design and the stack. And then there's another paper where we performed a user study. So that is at a very high level the Jacdac architecture. It's client server. There's a bus. We send packets back and forth asynchronously. And for more details, ask me questions at the end or see the paper. What I want to do now is give you a little bit more of a demo about Jacdac. And I see it's making its way around. So that's great. I hope everybody gets to see it. So let us do a demo. I'm going to go to the Jacdac website. So here's the Jacdac website. Oh, we can see it. So the microbit has a USB connection. So the Jacdac bus can be extended from the 3-wire protocol we have on the physical circuit over web USB into the web browser. And this is what I mean when I say that Jacdac has a modern stack. So again, with MakeCode, we don't want a C or C++ compiler to be installed. Similarly with Jacdac, we don't want device drivers and all that stuff to mess up the user experience. So what we're doing here is we've plugged the microbit in, and we're going to connect it over web USB to the browser that you see here. And actually, it's already connected. So what you see here from left to right is that we have a light sensor. So the light sensor module is here. When I cover it up, the digital twin on the left is showing me the value. So the first thing we have is discovery. You know, if I take the light sensor out of the bus, eventually, you know, it's going to disappear there, and it has disappeared. You know, I plug it back into any of the ports, and we are good. Okay, I have a slider, and the slider goes back and forth. Jacdac services are the abstraction by which all this happens, and I will give you just a brief tour of that. We have a service catalog with the abstract services defined in a mix of markdown and syntax defined in the PLDI paper, and that is shown here. So that the accelerometer is actually a register with 3 values, and you can see that we actually have units of gravity. We have the actual wire data value here specified. Furthermore, we have events. So a module can raise events as well as exposing registers over the network. You can also send commands to modules as well. So the Jacdac website has a whole set of devices, many of which are commercially available, as well as the tooling for device manufacturers to learn how to create new modules. So finally, I want to end with a very quick demo of how this gets then exposed in make code. So let me do that. So we're back in make code, and what we're going to do is we're going to attach. We're going to connect to the device that we have here. Oh, and I do need to remember one thing. One thing about Web USB is you only get one window at a time. They don't operate well when you try to have them both. So here we are. We're connecting to the microbit, and basically what's going to happen here, hopefully, is that we'll see the Jacdac stuff show up under the microbit. I'll just reload. There we go. Maybe that demo is not going to work today. Okay, we are going to cancel that demo. Oh, too bad, too bad. All right, we missed out there. All right, let me finish up, because I think we're running out of time. Are we back? Right. Okay, so we've built a number of Jacdac projects internally. We had an accessibility hackathon several years ago. Some examples there. Just in summary, Jacdac plug and play for prototyping with microcontrollers. We've sought to retain the low-cost, high-quality simplicity with the microbit, but extend it to a plug-and-play system. It's applicable to other platforms. We have adapters for Raspberry Pi and other hardware. It's all open source, both the hardware design and the software, and it's commercially available via third-party manufacturers. So thank you very much.
Thank you, Tom. We do have time for a question or two. All right. Have we got one coming from? No. All right. I'll happily ask a question.
Okay, cool.
That was an awesome talk. Very inspiring. As a long-time PLDI person, when you reflect on that project, what were the key PL-ish challenges that you found in doing that software stack you spoke of?
You know, that's sort of an interesting thing. I think the big thing about Jacdac is many design decisions together. Right. The language itself is an interface definition language. Part of the design goal there is to have a wire format that translates very easily to packets, right? And at the same time, have enough high-level abstractions in that so that we can generate the client code. So part of the language design was to sort of bridge this gap between wanting nice client code, event handlers, and things like that, but also supporting sort of the description of on-the-wire format. And then, you know, making that really optimizing the runtime and everything to work with, say, very low cost and low memory microcontrollers.
Great, thanks.
Hi, thanks for the talk. I thought that was great. I have a question. Do you have any sort of knowledge or experience of how people transition from using these sorts of tools, and particularly the programming environment, to more like real programming or electronics?
Yeah, I mean, that's sort of interesting. I guess one way to look at it is if you wanted to produce, like, if you did some prototyping and then you wanted to produce 10 or 100 of a device, you wouldn't want to do it with all these cables, perhaps, right? So then you would need to, perhaps produce a single PCB with all your components on it, right? So it's not just a matter of programming. I would say it would be a matter of also figuring out how to optimize your design, right? So we do have some research projects around that. So given you've done prototyping with Jacdac, how do you take the set of things that you want and make a device? In terms of the programming, our programming model is very much at a high level. It's event-based, and we hide a lot of the asynchrony from the programmer. So we have an underlying operating system, which is cooperative coroutines on a single processor. There's a lot of complexity hidden from the end user. If you want to start doing more things that are hard real time, you're going to have to learn. You're going to have to go down a few levels. So the type of things you build with us will get you only so far, and then you'll probably hit a wall. Is what I would say. The truth is, yeah.
Okay. Thank you.
Sure.
Time for one last quick question.
I don't know if this one is easy to answer, so maybe this one doesn't fit in the time. But I'm curious, I mean, it's had such a long history. I'm curious if there's something that when you tried revealing it to users, especially to kids, that ended up being sort of the most confusing and that you felt really had to be hidden under abstractions.
Oh yeah, it's not up here anymore. There was a super confusing thing. When we connect make code to the bus, originally we had 2 microbits on the bus. We had the real one and the virtual one. And both of them can be a brain. So now you've got all these devices and you've got 2 brains, and which one's in control? So this caused a lot of confusion. We had a lot of design discussions, and then we have a partner, Forward Education, that basically helped us out. So really, there is this big confusion that can happen when you've got the ability to put virtual devices on the bus as well as physical, and then you got a mix. So what we've currently done is, like, when your microbit is attached to the bus, the physical one is sort of the one, and then the microbit, the simulator, is sort of a pass-through. But there's a huge like design space there that's relatively unexplored from our viewpoint, and that was like we did a lot of trials with teachers and saw major confusion. It's like only one brain at a time.
That's really cool. Thank you.
That was the lesson. Yeah. Okay.
Thanks, Tom.
Thank you.